Okay, so today we're looking over chapter 11, looking a little bit at some extra unit 3 stuff. Um, but chapter 11 is pretty short. I'm going to say it now and I'll say it a few times. Make sure, I got that you're here. Make sure that you are reading this chapter, okay? There's a lot packed in, but it's a short chapter, so it won't take you a long time. But there's a lot that you'll probably want to look over because what we're doing in class isn't necessarily going to cover it. And class is going to be a little bit different today. First of all, we just took a unit test, so let's see what progress you've made. It's a little lame, it's a little fun, it's a little something, but let's see where we are. We've made it all the way down to the Little Colorado River confluence. So that we're not going to watch a video today. There wasn't any especially good video I could find, short one. So here's just a couple of pictures of that. We got the beautiful blue Little Colorado River meeting our Colorado River here. Here's an aerial view of that. So we've made it this far, kind of calm and serene, little moment to relax. Okay, so unit 3, this is what we just tested on. These are some questions I wanted to look at because they're ones that for one reason or another, yes, the TAs, you are good to go. Sorry about that. For one reason or another, I just didn't feel like these should go on the test. I thought there's just, and you'll see why. This one right here, it's another computer printout, but it's set up a little differently where it doesn't tell you the actual value in a very clear way. So we'll talk about degrees of freedom another point, but right now it's the estimate. That's what you would have looked, and maybe you would have known that, but anyways, the intercept and these are the same as any other computer printout, but the estimate right here would be the numbers. So from there, it's still the same thing. We're not going to go through the rest of the problem. This one, I needed to add a little bit of nuance to this because we talked about, and I thought this was a classic one that would trip you up. So anyways, let's kind of go through this. Which of the following statements about least squares regression analysis is true? So the first one, a point with a large residual is an outlier. Well, that seems like what we talked about, so I'm going to put a star next to that one. A point with high leverage has a y value that is not consistent with the other y values in the set. Well, that's not true because high leverage means it has an x value that's not consistent with the other x values in the set. The removal of an influential point from a data set could change the value of the correlation coefficient. Well, that is kind of the definition of an influential point. So yes, that one's definitely true. So it's this one up top I want to come back to. A point with a large residual is an outlier. That is true, but it's not 100% true. You can have a point with a large residual that is not an outlier. So let's say this is your regression line for a scatter plot, and you have a bunch of points right here, and then a point up here. Obviously, that's an outlier and it has a large residual. But if we change the scenario just a little bit, let's say that here's your scatter plot. Right? Now this has a high residual, but it's not an outlier because there's a lot of things with high residuals. All right, so just having a large residual does not necessarily make it an outlier. It's a large residual when the other points, you know, don't have that high of a residual. So that's one little distinction. I was like, that's a tricky problem, and I didn't necessarily talk about it in those terms. But hopefully now you understand why one is not correct. Okay. So the next one. This one is weird. It tells you mean and standard deviation of your x values, mean and standard deviation of your y values, and the question is which could be the least squares regression line, not which one is, and what it doesn't tell us is our correlation. So that's a mystery. But I do have S sub, or I'll put x bar, S sub x. So x bar is 5, S sub x is 4. Y bar is 10, S sub y is 10. So to figure out which answer here could be the regression equation, there's only one answer that works. There's a couple of things we need to remember. First of all, our slope formula is r times S sub y over S sub x. I can plug a couple of those numbers in. I know S sub y is 10. I know S sub x is 4. Of course, here's r. So that's 2.5 times r. And it might not look like we've made any progress, but we can say something now. I know that my r value has to be between -1 and 1. So if I plug that in to my slope equation right here, that means my slope has to be between -2.5 and 2.5. Those are the only values my slope can be for this problem. So knowing that, I can rule out A and B. These three have slopes that fall within that range, so I can't rule them out. And it might not seem like that's a lot of progress, but you know, it's a start, and it is going to be important for us to find our final answer. So that's taking care of the slope. One thing we can also do is we can remember that x bar, y bar always goes through, is a point that's on the regression line, always. So what I can do is I can take these regression equations that I still have as options, and I can plug x bar, y bar into them, see which one actually works. So y bar for C. So y bar is 10 equals 5.0 plus 2.5 times, and my x bar is 5. So if I do the math on that, 2.5 times 5 is 12.5, I'm sorry. 12.5 plus 15, so 10 equals 17.5. Okay, that's not true. So therefore, C doesn't work. Let's try D. So 10 equals 8.5 plus 0.3 times 5. Okay, again, I can plug that 5 times 0.3 is going to be 1.5 plus 8.5, 10 equals 10. It looks like D is my answer. I'll go ahead and circle that. But we'll try the last one as well. 10 equals 10 plus 0.4 times 5. Okay, I don't even need to do the math on this because I already start with 10 and I'm adding a positive number here. So I know it's going to be more than 10. So no, those don't equal. E doesn't work. The only one that works as a regression equation is D. Okay, now we had to consider this part about the slope because I didn't do it, but if I had plugged my two numbers into this equation right here, that would have worked out with the numbers, but the slope is not right. So anyways, we've ruled it down. Any questions on those? Okay, and we'll just move ahead. Hopefully that process made some sense. You're just using properties of your correlation and some equations that you know in order to figure out how to do this. Okay, this is a problem we're going to look at just to get started. And I'm not asking for an actual answer to this, but I just want you to consider this scenario for 30 seconds, a minute, however long it takes. Okay, again, I'm not asking for you guys to say, oh, here's the answer, here's how you solve, but do you have any initial thoughts on this type of problem?
Probably need to use probability of some kind, right?
Okay, and that's a good thought. And there are algorithmic methods for solving this. But we're going to approach it a different way. And when I say algorithmic, like there might be a formula we could come up with that we could then plug in some certain variables into. When we have the input, we can come up with the answer. And yeah, this is definitely tying into probability. And probability will be the next thing that we get into after this unit. That'll be a fun part, depending on how you feel about that. So you're on the right track. We are going to approach it a different way. And I'm not asking for any, if anyone has anything more to say, you can. But we will come back to this. Okay, so don't worry about it too much right now. First, we're going to talk about randomness. And this is kind of all this, the first part of randomness that I talk about is kind of a brief aside, but I think it's worth knowing. Okay, so what I have here are results from coin flips. So it starts at the top left and comes down and then goes to the next column down. So that's how you kind of read this chart. Looking at these two, one of these was produced by actually flipping a coin, and one of them was produced by me just making up results of flipping a coin. So knowing that, which one do you think, and you can just point to it, annotate on the screen, which one do you think is the real results? Okay. I'll give a few more seconds if other people want to provide some input. All right. And we'll just call that good. We're not going to spend like forever on this. So the real results were these over here. So a couple of you had that. Oops, I didn't mean to do that. So here's how randomness works. And this is why I think it's worth kind of looking at this for just a second. Real randomness means we could have lots of heads, I was about to say tails and I changed to heads. Anyways, lots of heads flip in a row. So 4 in a row, that's not actually that uncommon. Then we had 3 tails in a row, and then heads, tails, and then I got 6 heads in a row. Now, if you did this, if you flipped a coin 20 times, you might very well find that you get 6 heads in a row. But whenever we think we're creating randomness, we very seldom have a stretch that long because we think randomness means, oh, if I get too many heads, then I need to get a tails. And then I need, maybe do tails for a little bit, but then I have to switch back to heads. So we do this kind of back and forth when we're generating what we think is randomness. And it's just, remember that there's a name for this. This is what we call the gambler's fallacy, which says, if we see lots of heads in a row, we think, oh, well, that means it's got to be tails next. But randomness doesn't work that way. Anything that happened in the past has no bearing on what happens in the future. So 3 heads in a row, whatever. The next one, there's still a 50% chance it's going to be heads. And we can see with real results, we get 6 in a row, 7 in a row, 8 in a row. So anyways, if you're ever trying to identify if it's real randomness or not, look for these really long streaks or something that seems unusual. And if that happens, then you're like, you know what? I think that's real randomness. So that, just on a brief aside, another thing with randomness is when people try and draw stars, if they're painting and they want to have a night sky, a lot of times people just try and fill in the gaps and space the stars out. So if you're a painter and you're trying to paint a night sky, don't fall into this trap of just like, oh, there's a gap here, so I'm going to put a star. Oh, there's another gap right here. Go out and look at the real night sky. You'll see clusters of stars, like right here, and then a big nothing, and then a star over here, and then maybe 3 stars in a row here, and then just a bunch of nothing, and then you get the idea. So real night skies are very randomly scattered with stars. Okay. True randomness is almost impossible in the real world. Again, this is part of this aside that doesn't matter in the long run, but it's interesting to know. What we frequently call random is not random at all. So it's what we might call deterministic. It's unpredictable enough that from our perspective, it functions the same as true randomness. So what we're going to do for randomness in our class is not truly random, but it works. Okay, so of course we're going to talk about randomly selecting people for a study, but it's not true randomness, but that doesn't matter. Okay, it's random enough to be valid for our statistical assumptions. And there are some methods for creating randomness that's called pseudo-random. So we're gonna learn some stuff on the calculator. That's pseudo-random. Okay, and this is a definition from your textbook, but I like it. An outcome is random if we know the possible values it can have, but not which particular value it takes. Okay, so how do we generate randomness? We'll talk about sampling methods, which is important for us, but that'll be next chapter. So if given a specific event with known probability, if we wanted to generate random outcomes, we have a few options. One of them I forgot to make a slide for is we have things like spinners. So if you have a spinner, like in a game, you might have played one. So if you have a spinner, you could just spin that. That's random enough. A coin flip, you could do, roll a die. So there you go. I don't need to draw all this. You know what a die looks like. So rolling a die is random. Any kind of these, a deck of cards. So any of these things that appear that we use for random chance type stuff are useful if we want to simulate outcomes. But more practically, we have a couple of options. There's a random digit table, and you can see this came from your textbook. It's Appendix G. So I'm going to show you exactly how we use this later, but these table of random digits are produced. So when we say it's not real randomness, random means we don't know what's going to come after this 4 right here, but we do. It's a 5. So it's already set. There's no more randomness that's going to happen. We know what the digits are, but it can work to simulate randomness. And so these numbers could be like results. There's lots of ways of using a random digit table. So maybe if you have 10 options for something, then each number, 0 through 9, can represent one of the outcomes. So 9 represents something, 6 represents something, and so on. And we can kind of keep track. And we will use this in a little bit. It's important to know how to use a random digit table. But more practically, what you're going to be doing is using your calculator. And your calculator has a few things. It can generate a random integer. Random normal is interesting, but we're not going to talk about that now. And then random binary, random integer with no repeat. And I'll talk about how both of these 5 and 8 right here work. If you have the calculator from the library, if you choose random integer, and the way you get to that, I didn't explain, you hit the math button on your calculator. So just on the main screen, hit math, scroll to the right until you get to probability, and you can find random integer number 5. And it gives you an open parenthesis on your calculator. And what you want to do, you have 2 options for how we do this. One of them is I want to generate a random number between 1 and 25, including 1 and 25. So I want to get 1 and 25 and just generate a random number. So if you did that, or you could pick what your lower and upper bound are going to be. The comma is just above the 7. So I just did this and I got 15. And once I've got it set, I can just keep hitting enter and it'll give me different random numbers. But if you do this long enough, you're going to recognize that you're going to get the same numbers. Like I've gotten 12 twice and 15 twice in just a few trials. So let's say you wanted to do this, but you didn't want to have, or well, sorry, we'll jump to that in a minute. The other thing you can do is, let's say you want to draw 3 random numbers from the range 1 to 25. Then you add a third value, which is how many numbers are you drawing? 1 to 25 is your range. 3 is your number of points that you can see what the output would look like. So you can try that one as well. Nothing too complicated with this. All right, so if you're good with that, we can look ahead. Okay, I'll just do that. Were there any questions? Anyone having trouble with their calculator? If you have a newer calculator, you might have an interface that asks you for your lower and upper and how many numbers do you want, this and that. But most of us don't have an interface for this. Random integer, no repeat. The one thing you have to be careful of with this is that, at least on the TI-84 Plus, you can only put in what your upper and lower bound are going to be. And what it will do is it will take all 5 of those numbers and randomly assign them. So now you got 4, 5, 1, 2, 3, 3, 2, 5, 1, 4. Yeah, you can see the results here, but it gives you, it doesn't, you can't say pick a random number between 1 and 5 with no repeats. So it has to go through all of them because it's not going to remember after this which ones it's already used, if that makes sense. So be careful when you're using this. Don't do like 1 to 100 because it's going to give you 100 randomly arranged digits, and that will be a pain in the butt to look at. Okay. So any questions with random integer? If you hang out after the homework, I will go through a problem where I use random integer no repeat. Okay. So I haven't, with everything we talked about so far, we haven't exactly said how we're going to approach this problem. But now I just want to introduce the fact that we do have a way of generating random numbers. And I'm going to just draw your attention to the fact that campgrounds are assigned randomly. So maybe, are there new ideas about how we could approach this problem?
Use the random input.
Okay. So we can randomly assign things. I'm going to go ahead and skip to the next slide. And this gives a little bit of a clue. So really nothing's changed except I added these. So what number range could correspond to a campsite in loop A? And that might not make sense. 1 to, okay, I heard 1 to 10. So if I've got a random number that could be generated, what might correspond with loop B?
1 to 15.
All right, and this is where we're actually going to
10 to 25?
Not 10, it's close. It'd be 11 to 25. So what we're going to say is, this is kind of where we do our little trick. We figure out how many campgrounds do we have overall. If I add that up, 10 plus 15 plus 30 plus 40, how many campsites are there?
95.
95. So when I randomly generate a number, that's going to correspond with one of those 95 campsites. If I get campsite 1 to 10, that means I'm staying in loop A. If I get campsite 11 to 25, I'm in loop B. So what is loop C going to be? What range is that going to have?
$26 to $55.
There it is, 26 to 55. And then loop D is going to be what?
56 to 95.
There it is. Now, I mean, there was nothing special about this particular arrangement. I could have switched it up. I could have started with loop D and called that 1 to 40 and then labeled everything else. But, you know, this works as a way of doing it. So now what I can do is use, and this is where the calculator is probably the most useful tool for this, but we could just use this and we could randomly generate a number 1 to 95. And I'll kind of start going through this real quick. And we need to think about what the question is asking. How many times would I need to go to this campground until I camped on every loop at least once? So I don't care individually what happens the first time I go. In this case, I rolled a 93. So that means I just stayed in loop D. All right, but I am going to keep a tally. So I just went one time and I stayed in loop D. I just went a second time and I got 6 as my output. So I just got to stay at loop A. So that took me 2 times. Now I just got 49. So I just stayed at loop C. Took me 3 times. My next one, this is unusual. I got 2. So I just stayed at loop A again. And all I'm doing when I say I generated another number, I'm just hitting enter because it saves the 1 to 95 on my calculator. I set up random integer 1 to 95, and I keep hitting enter. So I'm just going to keep doing this. The next one I got was a 20. And sure enough, it only took me 5 tries. And I will tell you, this is kind of unusual that it only took 5 tries. So what I want you to do, are there questions on what I just did to get my answer? Okay, so if that idea, this is what we call a trial. I just did one trial. This doesn't mean my final answer is 5. It means that in one particular trial of the simulation, it only took me 5 tries. So here's what's going to happen on the next page. And I will clear this. I will add these numbers back up. 1 to 10, 11 to 25. This is 26 to 55, just so you can remember the numbers. And D is going to be from 56 to 95. So you're going to keep a tally of how many times it takes until you state it, all 4 of these campsites, or on those loops. And then you're going to add a dot onto this time, onto this dot plot. So it took me 5. I'm going to put a dot right there. So I will let you guys go through the simulation for one trial and add your dots to this. Okay, now we could keep doing this for the rest of class and just keep adding dots. And of course, in a real simulation, a simulation would be done by a computer, and it might be done 10,000 times. This website I mentioned, or I don't think I mentioned in here, 538, they do simulations on all kinds of things, including like the presidential election, how they think it might go. And what they're doing is this same idea, a little more complex, but they run like 10,000 or 100,000 or even 1 million trials with their computer, and they figure out kind of what distribution it takes. So anyways, what we would see here if we did this a lot is we would probably see something that looks like this. And you can start to see that a little bit. We do have a tail. We had someone that took over 25 tries to get, I don't know what that is, 26, 27, but anyways, we would start to see a distribution that looks like this. And it would center somewhere maybe around 9 or 10. So simulation repeated over and over will tell us normally where we end up, that measure of center. We would probably just look at the mode here. Okay, so that is a simulation. I'm going to clear all this because we're going to kind of get a little bit of understanding, and then I'm going to show you an example from the textbook. Okay, so this is just kind of some definitions and textbook knowledge, but it's good to know, kind of to debrief on it. A simulation models a real-world situation by using random digit outcomes to mimic the uncertainty of a response variable of interest. That's a pretty good definition, but it gets a little wordy. Basically, we know what we're trying to find an answer to. How many times did we have to go until we stated all 4 loops? And we're just using randomness to figure that out. Every data point that was added to the dot plot was a trial. So each simulated answer to our question is a trial, and you would go through many, many trials. Okay. The assignment of a campsite was a component in our simulation. It's the basic building block that makes up a trial. So we went and we were assigned a campsite, and we kind of kept track. Okay, and then we were assigned another one, and we kept doing this. Those are the components that make up our trial. And you have to kind of think through for every problem what your component is and how you would model that. And this is kind of the key to it all. The number of visits until every campground loop was stayed in was the response variable. And it's the number we collected and plotted in the end. So the key thing to this is, what actual data are we collecting? I'm not showing, oh, I stayed in loop A. Oh, I stayed in loop B. I'm showing the only thing I'm interested in that we plotted was how many times did we go until we stayed in all 4. So that's our response variable. Okay, and we'll talk about this a little more. So real quick, I'm going back to the random digit table. And this is something that you could very easily have a an FRQ where they ask you to describe a simulation you would set up using a random digit table. And I don't know if there will be an FRQ like that on your test for this, but just be aware, you need to be able to use a random digit table. So let's say we were doing the same thing. We had the same range, 1 to 10, 11 to 25, 26 to 55, and 56 to 95. So these were our ranges, and we used them before, we're using them again, but now it's a random digit table. And in truth, I could start anywhere. So let's say I started here with those numbers. So what I would do, and it's going to be kind of hard to show this because but I would start, because this is a 2-digit number that I'm interested in, I would start with that. I think I'd pick these right here. So I'd start with that 71. 71 means that I'm staying in campground loop D. Now, one thing we didn't talk about is if I get 00, I just skip that. It doesn't count as a component or a particular outcome. If I get 96 to 99, I skip that as well. It doesn't count. So I stayed on loop D. So there's 1. Here's loop D again. This looks like this is loop D. That's going to be loop C. So now I stayed there. I'm not going to go through this entire trial. Loop D again, loop D. Anyways, you can see we can just keep looking at the next 2 digits, loop D. These are randomly generated numbers, at least for our purposes. So 42, 55, 48. So it's going to take a while until I get all of them. I'm not going to go through how many trials that is. But we can add it up. Let's say we finally get to the end. We can say, okay, here's 1, 2, 3, 4, 5, 6, 7, ... However many it took as I go through the random digits. And then I can come up with my response variable. Oh, it took me 13 trips. I don't know what it is, but we'll just pretend it was 13 trips. So random digit tables can work the same way. It's just important that you know how to use them. Okay, any questions on the random digit table? Okay. This is an example from the textbook. So you can go back and review this one, but I thought it was just really good how they laid it out. So there's a game of 21. It's not blackjack, but it's similar to it. But you play with a 6-sided die. Competitors roll the die, trying to get the highest total less than or equal to 21. If your total exceeds 21, you lose. So let's say that your opponent has rolled an 18. You are trying to beat them without going over 21. So here's the key to this. How many rolls do you expect to make, and what are your chances of winning? They're asking 2 questions here. We have 2 response variables, and that'll come up again, but I just want you to be aware. Look at the question that's asked and understand, what are we keeping data on? How you simulate the components? Well, if you're not actually going to roll a die, which would take a long time, you can just simulate by looking at a random digit from a table or from your calculator. And if it's your calculator, you can just make it 1 through 6. If it's a random digit table, you can ignore 7 to 9 or 0. Those don't count as rolls. So how are you going to combine your components to make a trial? And what's the response variable? So you can add your components until your total is greater than 18, counting the number of rolls. If my total is greater than 21, it is a loss. If not, it is a win. There are 2 response variables. Counting the number of times I roll the die, that's going to be 1, and keeping track of whether I win or lose, if you had a winning score or losing. So there's a couple of trials. We'll just run through how this works in practice. Here's the random digit table. So they started with a 9. You can see the 9 right here at the beginning. So that doesn't count as a roll. We don't add it into the total. Then it was a 1, 1, 2, 9, 5. You can see the results, and you can see where they come from the random digit table. So you can see that you can keep track of how many times there were. We had 1, 2, 3, 4, 5, 6 rolls. And out of that, when you add the cumulative total right here, it got up to 20. So that counts as a win. It's over 18, less than 21. Or 21 or less, I should say. So anyways, it was a win, and it was 6 rolls. Going through, now that ended at this 6 right here. So if we start with the 9 that's after that one for the next trial, again, that doesn't count. So same process, but now we've got 1, 2, 3, 4, 5, 6, 7 rolls. And it went to 23, so that is a loss. Okay, so when we tally this up, we can say, here's how many die rolls it took, and here's the win-loss record. So this is, if you ran 30 trials, what is your conclusion? Based on my simulation, when competing against an opponent who has a score of 18, I expect my turn to usually last 5 or 6 rolls. You can see the mode right there. And I should win about 70% of the time. If we add up these tally marks, this is 21 wins. That's 9 losses. So 21 out of 30 is that 70%. Okay, and I can't emphasize this enough. It is really encouraged, and I would say really important that you guys go through and read this chapter. I kind of said that before the test yesterday, but I didn't advertise that a whole lot, so I don't know how many of you actually read it. It's a short chapter, only 5 pages, but there's a lot of good information in there. So we'll just, of course, just to repeat that point, there it is. Now there's a couple of things in the chapter that are worth focusing on. I didn't reproduce this on the presentation today because it's in the textbook, really well done. Page 258 to 259 shows kind of this, I think, 8-step, 9-step process for creating a simulation. And then the step-by-step example, page 260 to 262, is another really good one that kind of walks you through every step. If you've been following these step-by-step examples in the book as you're reading, you might find them really helpful, and this one is another good example. So read, now I should have in here read chapter 11, because I bet a lot of you haven't done that yet. But tomorrow we're going to be looking at chapter 12. Make sure you're reading that as well. Your homework tonight is all this. It's, again, on the Canvas page. The only one you have to turn in is number 15. So make sure you're actually submitting that for your homework at some point before the test. Okay, that is it for today. I am going to go through one practice problem from the book. So if you want to stick around to see that, you can. And otherwise, have a wonderful day. Okay, and I'll go ahead and get started on the example from the book. And here's the situation. A new electronics store holds a contest to attract shoppers. Once an hour, someone in the store is chosen at random to play the music game. Here's how it works. An ace and 4 of the cards are shuffled and placed face down on a table. The customer gets to turn cards over one at a time looking for the ace. The person wins $100 worth of free CDs or DVDs if the ace is the first card, 50 if it's the second, 20, 10, and 5 for third, fourth, fifth. What is the average dollar amount of music the store will give away? Okay, so this, it looks somewhat complicated, but here's how I'm going to set this up. I know in this particular case, unlike that last one with the campground loops, I could be assigned to the same campground twice in a row. But here, I can't draw the same card twice in a row because once it's drawn, I can't get it again. So this is going to be random integer with no repeat. So in my calculator, I'd go to random integer, no repeat. And I'll go ahead and write this down. Rand int, no repeat. And I just want to think, I've got 5 cards. So if I just decided to go from 1 to 5 with my no repeat, then I've got all 5 cards modeled. And what I need to decide before I start doing trials is, what is the ace going to be represented by? And I will decide that a 1 is the ace. All right. So before I start running the trials, I just need to create a like tally sheet for myself. It could be first, second, third, fourth, or fifth in order. And I'm just going to tally where it shows up in order. So if I go ahead and run this rand integer no repeat 1 to 5, then in my first trial, the 1 showed up second in my list. And now all I have to do is keep hitting enter. In the second trial, it showed up second again. And the way I'm finding that is I'm just looking at the numbers. So my first trial is 51432. The next one is 51324. So 1 was second in the list both times. Third try it was third. Fourth try it was second again. Wow. This is, now it's fourth. Now it's fifth. And every time I add another tally, I'm just hitting enter on my calculator again. So it showed up second on that trial, showed up fifth. Now we could do this an awful lot. I don't know how many trials I'll do. But I can just keep hitting enter and putting a tally where it should go. Hasn't shown up first yet. Oh, there it is. As soon as I say something. It's really liking showing up second. All right, I might do like 10 more trials or so just to see kind of what the trend looks like it's being. All right, maybe 3 more. 1, 2, oops. 3. All right, and this shouldn't exist. Okay, so I could keep going, but what I hope is showing up if you're doing this at home, I hope you're seeing that it kind of distributes pretty evenly. And if you did this 1,000 times, 1,000,000 times, you'd probably end up with a pretty even distribution. So all these would kind of tally close to the same amount with enough trials. So anyways, that's kind of theoretically what would happen. But let's just go ahead and figure out, let's say these are my results. I want to figure out what the average amount given away was based on these results. So yours will be different, but you can kind of see what I'm doing. If it showed up first, they got $100. So that's going to be 4 times $100. Plus, I had 8 times it showed up second, and that means it's worth $50 there. Plus 3 times 20, plus 5 times 10, plus 5 times 5. Okay, and this math, you could plug in your calculator. I'll just do it real quick. So that's 400. That's 400. That's 60. That's 50. And that's 25. So add that all up, 800 to 910, 935. $935 was given out. And now I want to figure out how many trials did we have? Well, there were 4 times here, and then 8. I already did this, but I'll just do it again. 3, 5, and 5. So to add that up, there were 12, 15, 25. I did 25 trials. So if I divide 935 by the 25 times that we did this, the average amount was 37.4. Okay, now as long as you have your data and you're showing all this, the exact answer you get just needs to make sense based on the data you collected. If we did this often enough, what we'd find is the true average would be right around $37. So I actually came really close to the true average. And when I did this in my 5th hour class, we were getting a lot of 1s and 2s, and I ended up with 52 as my average. But anyways, if you do this trial, like a sequence of this trials on your own, you might find you're above or below or right at 37. And that is where it would end up if you did a lot of simulations. Okay, so that's basically how we'd approach this. And that's really all I've got for today. So if you have other questions, I can try and answer those. But otherwise, that's what I've got for you today.